Hello and welcome, I'm your Code Monkey, and in this video let's do a nice simple project to check out the current state of Unity Dots. Version 1.0 is finally here, although still technically in preview. It's going to be fully released production ready in the 22 LTS stream, which will happen sometime early next year. But since version 1.0 is now here and leaving experimental very soon, that means the API probably won't change too much until the final production ready release. So while you probably should not be using this in production just yet, it is in an advanced enough state that you can absolutely start learning it. If you're watching this video sometime in the future, most of it should still be up to date. So here let's learn the basics of how ECS 1.0 works. The great news is that if you've played around with ECS just like I did 2 years ago, then nowadays everything is a lot simpler with a lot better tools. Now, I initially wanted this video to be just a pretty quick overview, something about 15 minutes long, but I felt it would be a bit of a disservice to you to simplify things so much just to fit a short length, so it ended up being quite a lot more detailed and quite a bit longer than I anticipated. If you find the video helpful and you want to help me out, you can wishlist my game on Steam. It's called Total World Liberation, features lots of interconnect systems, and I'll probably be using dots in the final game. Or you can get my complete step-by-step courses, like my Ultimate Unity Overview, or my turn-based strategy course, which is actually the base for my Steam game. If you know absolutely nothing about dots, you can go watch my quick explainer on the theory behind it. That video is still up to date in terms of explaining all of the core concepts from a high-level view. As a quick refresher, the Entities package, or ECS, stands for Entities, Components, and Systems. Entities are basically just an identifier. Components are where you store the data. And finally, systems do whatever work you want on that data. So here let's build a super simple demo. We're going to set things up to have a simple character just spawn and randomly move around. Doing that involves learning about quite a lot of parts of ECS. So we need to create the entity, look into the conversion workflow, create a component to store the target position, use the baking system, create a system to generate a random position and move it. I will also cover how to mix ECS and Game Objects. So this is an excellent simple demo to showcase the absolute basics of how ECS works. And of course, in the end, I will showcase the performance comparison between ECS and regular MonoBehaviour code, as well as give you some resources if you want to dive deeper into dots. Alright, so let's begin. First, we need to install the packages. So let's go into the package manager, and up here, let's click on the plus, and let's add a package by name. And for the name, let's go with com.unity.entities. Let's add this one. And yep, there you go. It installed over here the entities package, as well as all of the required dependencies. So we've got burst, we've got mathematics collection, and so on. Now another great package we can add is the graphics package. That's what used to be called the hybrid renderer. So let's go into add package by name, com.unity.entities.graphics. Let's add this one. Okay, so with this we have all the packages we need. Also important is what it says over here on the documentation. The way this version of ECS works is heavily based on code generation. So you should be using an IDE that supports it, like for example Visual Studio 2022, which is what I'm using. And they also recommend that you modify the domain reload settings. This helps the editor be quite a lot faster by not reloading the current domain. To change that, just go up here into Edit, then into Project Settings. Then on the side, let's go into Editor, and over here, let's scroll down until we find over here the Interplay Mode settings. Make sure that this one is enabled, and make sure these two are unticked. So just like this. However, like it says here, be very wary that using this option means that your static fields will not automatically reset. So keep that in mind. You can read the docs to be more familiar with what exactly this option does. Okay, so now let's begin making a simple entity. And if you, like me, used dots 2 years ago, then you're going to be very pleased with how easy it is nowadays. How you do it is super simple. Let's go over here into the hierarchy. Let's right click and let's create a brand new subscene. So let's create an empty scene. Then over here, just give it a name, like for example, Entities Subscene. And if there it is, we have a subscene, and this little toggle here lets you enable or disable the subscene. And then over here, a bunch of options for opening or closing the subscene. But right now, let's leave it open. Basically, what this does is anything inside the subscene will automatically be converted from game objects into entities. So let's add a very simple new game object in that subscene. So let's right click on top of it, and over here, game object, let's create just an empty game object. Okay, that's it, just a super normal, regular game object. With this, if we hit play, we can see the object is over there in the hierarchy, and now if we look over here on the right on the inspector, right now as you can see it's normal, so it's showcasing a normal game object with transform, everything is perfectly normal. However, now if we look over here on the top right corner, we see this little circle icon. Basically, just like this, it's currently showing the regular game object inspector. And if we click on it, it goes into this half mode. I'm honestly not entirely sure what exactly this one does. It's supposed to be kind of a mixed mode, but it doesn't seem to change anything at all. And if we click again, there's actually a slight bug where sometimes this one does not update, but we can easily fix it. Let's just select another random game object and then back to selecting that game object. And now if we click, go into mix, click again, and yep, now this showcases the entity inspector. With this, we can see that the game object that we created was automatically converted into an entity. So yep, that's awesome. As you can see, this is how easy it is. We just created an empty game object, a normal game object in the subscene, and it automatically converted into an entity with all of the required default components, like for example over here the transform. Now let's do something even more special. Let's add a simple visual. So on the game object, let's right click on top of it, and inside let's create a new 3D object. Let's make a simple capsule. Let's just lift it up a bit off the ground, so something like this, and just give it a nice fun visual. Alright, there it is. Again, note how we're using regular game object components. So you've got a regular game object with a regular transform, a mesh filter, a mesh render, just like you have in any other game object. Then by default it comes with a capsule collider. Let's just remove this. We're not using physics in this demo. Okay, so just with this, let's hit on play. And yep, the object is there. Now there's also another entities hierarchy. So we can go over here into window and go down into entities, and let's open up the entities hierarchy. And that opens up this window, which again also has this nice circle button. So over here we are seeing all of the game objects. And we click on it, it brings the mix mode, click again, and now we see all of the entities. Note how the icon's here, so this little icon, the regular cube, that means a game object, whereas this one, this hexagon, means an entity. If we click on this, and over here look in the inspector, make sure you are in the entities inspector mode, and yep, we can see this game object, and the child was indeed fully converted into entities. So this game object, which is the parent, as you can see, has a child component, and inside has a reference to the child. Again, this is an entity reference, not a game object reference. And if we select the capsule visual, yep, over here we see that it has all the components required to actually render an entity. Okay, awesome. So it literally is that simple to make an entity and add a visual to it. You just make a new subscene, add a game object inside it, optionally add a visual, and that's really it. Everything is automatically converted. This process is much simpler than the previous method, which involved tons of boilerplate code to get anything rendered on screen. So now that we have our very simple entity, the next thing we want to do is just store some data, so we do that with components. Let's make a brand new script, so in my scripts folder, just right click and create a regular new C# script. Let's call it just speed, and open. Now here on this script, for making a component, first of all, it needs to be a struct, not a class, so this one is going to be a struct. And secondly, it does not extend MonoBehaviour. Instead, it needs to implement iComponentData. This one, as you can see, exists inside of the Unity.Entities namespace, so import that as well. Alright, so that's it. This is our very basic component. Now over here we can add whatever fields we want. So for example, let's add just a public float, just call it value. Okay, that's it, super simple. Now we want to add this component to our entity. And the way we do that in version 1.0 is through the baking system, which is a conversion that we just saw. Since this component does not extend MonoBehaviour, we cannot add it directly to our game object. So we need to make a separate MonoBehaviour, which will then be used to convert and create into this speed component. First over here, let's create a new C# script, call it speed authoring. By the way, adding the authoring suffix is not required, but it is a nice convention to follow. So let's open this. Here for this one, we are indeed going to leave it as a MonoBehaviour. And then we're just going to essentially add the exact same fields. So let's add a public float value. However, just like this, it won't work just yet. The system does not know that this MonoBehaviour belongs to this speed component. Right now, it doesn't know that connection is supposed to exist. So how we make that connection is by making a baker. Now you can make it in a separate script, or we can just add it over here right next to the MonoBehaviour. Since these are tightly connected, it makes sense to place it right here. So let's make a public, a class. Let's call it the speed baker. And we're going to extend baker of type, and let's include the type speed authoring. And baker, as you can see, is inside using Unity.Entities. Okay, so with this, we need to implement the abstract method. So let's implement that one. So here it is, the bake function. And from here, we can easily add component. And let's add the component that relates to our authoring component. So let's create a new speed, the speed component. And let's construct it with the value and grab the value from the authoring.value. Okay, so just like this, again, we have our regular component. So this one has no MonoBehaviour, it's not a class. Then we have the speed authoring. This is MonoBehaviour that we attach to our object. And then we've got a baker, which essentially grabs a reference over here of our speed authoring component and simply grabs that in order to access the value in order to set the value on the speed component. Now, this is the one part of the system that still feels a bit too needlessly complex. There should be some way of automating this if the MonoBehaviour is meant to have the exact same fields as over here the component. From what I read in the forums, they are actively working on simplifying this process. Apparently, it just didn't make it onto the 1.0 version. Okay, so with this done, if we go back in the editor, over here, let's select our regular game object and let's attach the speed authoring component. And over here, we can add whatever value we want. Now, if we hit on play, and let's go into our inspector into entities mode. And if we scroll down, yep, over here we do see our component, our speed component, and the value, yep, it does have the value that we set. All right, awesome. Okay, so far so good. Next, let's make a system to move our object. And when it comes to systems, there are two ways you can make them. You can make a class that extends SystemBase, or you can make a struct that implements ISystem. Essentially, SystemBase is meant for managed systems, and ISystem is meant for unmanaged. So that means that SystemBase cannot use the BurstCompiler, whereas ISystem can. If you're doing some super basic code where you want it to run just on the main thread and maximum performance is not necessary, then you can use SystemBase. But if you want the absolute max performance, then you should be using ISystem. Don't worry, I'll showcase both methods. For starters, let's use the SystemBase. So let's create a brand new C# script, and for this one, let's call it the moving SystemBase. Now inside, instead of a MonoBehaviour, let's extend SystemBase inside Unity.Entities, okay? And on this one, we need to implement the abstract function, the onUpdate, so let's do that. Now, just like this, if we save and we go back in the editor, yep, over here we do see a nice error. It is telling us that everything that extends SystemBase must be defined with the partial keyword. Again, this is due to how Dots 1.0 handles a lot of things based on code generation, so we need to make this partial. So up here, let's make this a public partial class. Okay, just like this. We don't have any errors, great. Now here, our goal is to move our entity. And for that, we're going to want to modify the entity position. And there are two ways we can do that. Let's look at the entity as it exists by default. Also, by the way, you don't need to head on play in order to see what the entity is converted into. If you're just like this with the game not playing, you can still go over here in the inspector and swap it out for entities mode. Again, we got this bug, so we can just swap out the game object, select that one, and then click again. And yep, there you go, we do see the conversion. So if you just want to see what this game object will be converted into, you don't need to go into play mode. You can see it directly over here. So as I was saying, we want to move, and to do that, there are many ways we can do that. And looking at the entity, by default, we can see it has a local to world transform. So one way to move it would be to access this component and modify over here the position. That would work, but modifying this position directly sometimes can cause some issues if the object is a child of something else. So it requires a bit of validation, a bit of extra logic rather than just setting this directly. And to solve this problem, that is where a brand new concept in Entities 1.0 comes in. That is the concept of the aspect. If you look over here in the inspector, up top we do see a bunch of buttons, so we see the components, is what we see, and then we have the aspects. By default, we can see that it does have a transform aspect holding the local position, local rotation, and the uniform scale. So this one is essentially the same as the regular transform. What an aspect basically is just a way to group together several components in a nice logical manner. So this transform aspect holds all of the logic related to a regular transform, so the position, rotation, scale, as well as a bunch of functions for working with those. We can actually inspect this built-in aspect to see what it does. So in the project, let's search for TransformAspect and make sure that we are searching over here in packages, and let's open up the transform aspect. And up here we see what it does. It implements the aspect interface, which again, we're going to cover this in a little bit. And then importantly, it has a bunch of helpful properties as well as functions in order to interact with this object. For example, we have a nice function here to translate the entity. It just receives a float 3 and then does the logic based on whether it's apparent or not. So again, aspects are basically a nice layer of abstraction, so you can combine multiple components and do some custom logic, which then allows your code to be much more simplified when you're doing regular things working directly with the aspect instead of the components. Don't worry if aspects seem a bit confusing now, it's only going to become quite a bit more clear once we make our own. So going back into our moving SystemBase, over here let's find all of the objects with that aspect and let's move them. And actually over here there are mainly two methods we can use. One of those is what is called the Entities.ForEach. If you've used dots in the past, then you're probably familiar with this method. But nowadays in Entities 1.0, there is another method, which is the one that you should be using. It is called the Idiomatic Foreach. So you do a for each just like you do in any other C# code, so just a regular for each. Then the type, so for now we want to move, so let's use the type for the TransformAspect, which again is over here inside using Unity.Transforms. So we do for each in, and then we do a query. So let's access the SystemAPI, and let's do a query, and we're going to query for the type that we want. So in this case, the TransformAspect. All right, so here it is. As you can see, super simple. Just a regular for each like you've always done in C#. Now with this, the code that we write here will run on every update for every single entity that has a TransformAspect. So for now, let's just move it to the right. So let's just access the TransformAspect and into the position, and let's increase the position. So we take in a float 3, which by the way, if you don't know, this is essentially a vector 3. It's just made with the Unity Mathematics library, which is meant to be more performant. So let's use this, and let's actually use our using up here. So up here, using this, and we're going to construct a new float 3, and we want to move to the right, so let's do just 1, 0, 0. Although again, this is going to run on every update. So in order for movement to be frame rate independent, we really should be using time.delta-time. So instead of being just 1, let's use time.delta-time. Although this time is not the one that you should be using. When working in ECS, you should be using SystemAPI.time.delta-time. Okay, so that's really it. With this, every single entity that we have that has a TransformAspect should be moving to the right at a speed of 1 unit per second. Also here I should point out, just like we saw, the TransformAspect has function, so if you don't want to add directly to the position, over here you could just use translate in the world, then pass in the same vector 3. So again, many options just like you have with regular transforms. Okay, so this is all you need to do in order to move an entity. And just for clarity's sake, let me quickly show you how the Entities.ForEach works. So here are both methods. Basically, they are extremely similar. With the Entities.ForEach, instead you have a lambda instead of doing a regular for each. So you have there, then over here you put whatever components you want, just like over here we're doing a query. And the one big difference is how in Entities.ForEach, at the end over here we need to call either schedule or schedule in parallel, or we call run. Basically the Entities.ForEach, this one returns a job, so then that job needs to be either scheduled or run. And what these three options mean is that basically run, this one runs the code just on the main thread. This one runs the code in a single worker thread, or alternatively schedule in parallel. This one runs the code on multiple worker threads. Whereas over here, when using the Idiomatic Foreach, over here you don't have an option. Everything over here is going to be run on the main thread, so it's exactly the same as doing run. That is why I previously mentioned that when using SystemBase and the Idiomatic Foreach, you should only do this for more simple use cases. If you want absolute maximum performance, then you should be using ISystem along with some proper jobs that can be parallelized, which again I'm going to cover in a little bit. Now, one more difference is that over here, the Idiomatic Foreach, this one can have multiple nested cycles. So you can do this. For example, this is a valid nested cycle, whereas with Entities.ForEach, you cannot nest them. Okay, so like I said, those are the differences, but now as of Entities 1.0, you should be using the Idiomatic Foreach, so let's get rid of the Entities.ForEach. So just with this code, let's test. And yep, there it is, the entity moving. All right, awesome. We can even select it, and again, look in the Entities Inspector, and yep, look at that, the local position constantly increasing on every second. Also, another thing we can look at is go into Window, then go into Entities, and down here look into the Systems window. And that opens up this nice window. Let's just anchor it down here. And we can view all of the various systems and how they are organized in various groups. And if we look, by default, if we look over here in Update in the Simulation System group, if you look here, we do see our moving system base that we just created. And yep, we can see that it is currently running. Okay, so now instead of moving at this speed, let's use the speed data from our component. Let's just use a proper speed. So over here, let's say put it a bit faster, but just on 2, okay. Now how we use our speed is super simple. We just add over here yet another field. So first on our query, let's add the speed component. And then over here, let's put this inside parentheses so we can add multiple. And let's add TransformAspect and then our speed component. So here when moving, we can simply use it. So our delta time multiplied by speed, and we grab the value. Also one more thing, which is up here in our query, we can define if this is going to be a read-only or a read-write component. So we can add the RefRW. So this one, RW stands for read-write. but in this case, we're just going to read the speed, so we can use RefRO, which means reference read only. So let's use this and also modify the value up here. So this one is the RefRO for our speed. And then we access speed, we access the value RO, and then access the value. Okay, so let's see if it's moving twice as fast. And yep, there it is. And by the way, over here, you can also modify it in runtime. So currently moving at this speed, if I put this on 3, yep, there you go, moving quite a bit. Put it on 0.1, there you go, moving really small. So that's one of the benefits of ECS, is you can easily edit any values at runtime. Okay, so the movement is working. Now let's make another component to define our target position. So in our project, let's make another C# script. Let's call this the target position. And over here, this one is going to be a component. So once again, let's make this a struct, and we're going to implement iComponentData. Then over here, let's just add a float3 for our value. Okay. Now let's quickly make the authoring component and the baker. So over here, let's create a new C# script for the target position authoring. And over here, this one is a MonoBehaviour. Let's add a public, a float3 for the value. And then we've got another one for the target position baker. And we extend baker of type target position authoring. And then over here, we simply implement. So let's first of all add using entities, and let's implement the abstract class. And over here, we're simply going to call our add component, and let's add new component of type target position. And inside, let's add the value to authoring.value. Okay, that's it, super simple. Now here in the editor, let's add the target position authoring. Let's also put it on a regular speed. And for the value, let's make it move up. So let's put it just on a Z of 5. Now back into our moving system base. Over here, let's add our brand new component. So over here, we've got our components in our query. So for the query, let's add another one. So let's add, in this case, we're actually going to be updating our target position. So let's make this an FRW. And let's add the target position. And then up here, let's add a RefRW of our target position. So here it is, some simple movement code. So we've got our target position, we subtract our current position in order to calculate the direction. We use math.normalize to normalize that vector. And then as usual, we just move along this direction with time.delta and using our speed. So let's see if it is now going towards the target position. And yep, it is indeed going up instead of going to the right. So let's put it to speed a bit faster. And let's modify over here target position. Let's move it a little bit to the right. And yep, there you go, it does. Move a bit backwards. And yep, there you go, it does work. Okay, awesome. So all of our logic is indeed working. But as we can see over here, we're getting quite a lot of components over here in our system. So with this is the perfect example to showcase the benefits of making our own aspect. Like I said, the main purpose of aspects is to group components into one logical unit. Over here, we are grabbing 3 components, and we're using all 3 in order to make our movement logic. So let's refactor this code with a nice aspect to help make this code quite a bit more clear. First, in the editor, let's add a new C# script, so a new one. Let's call it the move to position aspect. Then over here, the first thing that we're going to do is instead of MonoBehaviour, we're going to extend IAspect, which is inside Unity.Entities. And in order for it to be an aspect, it needs to be a struct. Then we see a nice error telling us that an aspect must be a struct and also must have the partial keyword, so let's add that. Finally, this one must also be marked as read-only. So read only. Okay, so that's our basic aspect definition. It needs to be a read-only partial struct and needs to implement IAspect. Now over here we can add whatever components we want. It can be regular components or they can also be other aspects. So for example, let's begin by adding our TransformAspect. So just a regular TransformAspect. And all of these fields must also be read-only. Then we can add components. So in our system, we were using the speed component, so let's add that as well. Except inside an aspect, we cannot use the component directly. We need to use one of these. So it needs to be a read-write, read-only, or enabled read-write, enabled read-only. So over here for the speed, like we saw, we're only reading, so let's add a RefRO of this. The other one we were using was the target position, so let's use a private read-only. And for that one we were writing, so RefRW of our target position. Finally, in our aspect, we can optionally add an entity field. So over here we can add a private read-only entity for our entity. This one is optional, you don't need to add this. But if you do, it will be automatically filled with whatever entity is currently running this aspect. One important thing is you can only have one, so if you have multiple entities, you get an error. So you can only have one field of type entity. Okay, so here we have our nice aspect, and now if we go back into our moving system base, over here instead of doing a query for all of these components, instead of that we can simplify this and just use our nice aspect. So just like this, our move to position aspect. So there it is, you can see the code is much simpler. And now if we want, we could expose all of the same components from the aspect, or since the whole point of the aspect is to group together logic, then we can just make some functions there. So let's copy this code. Let's go into our aspect, and over here let's just make a public void move, and in here let's paste the exact same code. So you do the same thing, we access the target position, calculate the direction, and move our transform aspect. Then back into our moving system base, over here instead of doing all of this, we just go into the aspect, and we call our move function. Also, one important note is over here, whilst inside IAspect, over here we cannot use the SystemAPI directly. If we try running the code like this, we see this error, which is not very helpful, just invalid operation. But really in this case, what that means is that we cannot use the SystemAPI to get the delta time whilst inside the aspect. So instead, let's modify this code, and let's receive over here a float for the delta time, and then we just use that one. Okay, just like this, so we receive that as a parameter. And on the moving system base, over here we can indeed use SystemAPI.time.deltaTime. Okay, let's test. And yep, now it does work perfectly. Okay, awesome. As you can see, with all of this, our system code is extremely simple, just a handful of lines of code. Same thing for the aspect, again, a really small file, everything is super simple, super easy to understand. And same thing for all of the components, all of them are pretty simple. So many files, but all of them are extremely simple, extremely easy to follow. This is one of the main benefits of ECS, is how the architecture forces you to essentially write good, high-quality code. Everything is nicely decoupled, nicely separated into separate files, each doing just one thing. Alright, so let's continue. When we reach the target position, we want to move to another random position. For testing when we get there, we can do a simple distance check. So we can do a math.distance. Also, by the way, in production code, you probably should be using the distance squared, since that one is a little bit faster. But for this quick demo, let's just use a simple distance just so our units make sense. So this one just takes our 2 points, so let's use the TransformAspect.position, and let's use the target position.valueRW.position. Okay, so if the distance is under a certain amount, so if we get there, then we want to generate a new random target position. Let's make a nice function to generate this. So public going to return a float3, get random position. And now usually what you would do would be something like this. So a new float3, and then let's randomize. So let's use the UnityEngine.Random in order to randomize between 0f and let's say 15f. Then no random on the y and another random on the z. So this is what we would normally use, but when working with dots, we cannot use the random.range. This is a class which would break when we eventually try to use bursts. So we cannot use this random class, but we can use the one inside the mathematics library. So we can use this random inside unity.mathematics. However, this one works differently. For this one, we need to initialize it. We need to do something like new random, which then takes in some kind of seed. And then we can use this random, which again, note how this one is a struct. So we can use this one in order to generate a next float. So we can do something like this. But again, the way this works is this receives a seed over there in the constructor. If we were to do this, then all of them would get the exact same random position because we were creating the seed and then generating exactly two numbers. So if we use it just like this, then this would return always the exact same random position. In order to make something properly random, we need to essentially store just a random instance, store this somewhere, and then reuse it to generate all of our random values. So again, back into how ECS works. how we hold some data, and random is indeed a piece of data. We hold this in a component, so let's make a component to hold this. Over here, let's create a new C# script, call it the random component. Now, as usual, let's do the same thing. So this one is an I component data. And then in here, we're just going to store a random. Again, make sure you use the correct type. So that's Unity.Mathematics.Random. And let's call it just random. And again, component is not a class, but rather a struct. Okay, so we have a random component. Now you might think that to add this, you could just make a authoring component just like we did, and then essentially attach it to our entity. However, if you did that, every single entity would add a random component. And if you use the same seed for all of them, then again, you would not really have any randomness. So what we want is not one random per entity, but just one random for the whole world. For that, we can use a really nice entity singleton. So let's first of all make a baker, which we're going to attach to a different object. So let's create a new C# script called the random authoring. Then over here, let's make the regular code, although in this case, we don't even need any fields. Alright, so there it is, super simple. If you wanted, you could input the seed over here if you want to customize the seed on the authoring component. And in the final game, you probably would want to use a proper seed, like perhaps the current time, but for testing, a nice fixed value works great and is actually quite helpful for debugging. Okay, so we have our component. Now over here, let's create an empty new game object on our entity subscene. Let's call this our random. And over here, let's attach the random authoring component. Okay, so with this, we have just one entity in the world with our random components. Now we just need to somehow use that over here in our random position. Now, since we made it a singleton, so there's only one random in the entire world, since we made that, we can easily access it. So we can go into the SystemAPI in order to get the singleton of type random component, and we have access to it, and then we can grab our random object. So this is how we can grab it. However, again, like I mentioned previously, we cannot use the SystemAPI whilst inside an IAspect. If we run this, we're going to see the same invalid error that we saw previously. We can only call the SystemAPI from our actual system. So instead, let's receive our random as a parameter. So let's receive this as our parameter here. Then over here in our move function, we're going to have to generate. So let's set this one. So let's receive it as a parameter over here as well. And when we reach a new position, let's set the new one. So we just set this one equals the getRandomPosition, and let's pass in our random. Okay, so all we need to do is pass in the random to the move function. So over here in our system, let's grab it so we can access the SystemAPI to get the singleton of type our random component. And let's access the random. So this is the Unity.Mathematics.Random. So we grab this one and then we pass it into our function. Okay, so with this, everything should be working. We no longer have any errors. So we pass in the random to the move function. Then the move function takes in the random and uses it to generate a new random position. Except this is not really going to work, but let's test and see what happens. So here we are, and the unit is indeed going to the target. Okay, great. And once it gets there, it generates a random position. Great. But now, as you can see, it's stuck in that position. We can test and see what is actually happening. Over here on the move position aspect, let's do a debug.log to see what value is being randomly generated. So let's do a debug.log on this. Okay, let's see. Ideally, it should always be different. It should always be random. So let's test. So it's playing, goes to the first position, gets there. Okay, generates another position, gets there, and nope, there you go. There's the issue. As you can see, the random is always generating the exact same position. So we have something going on with our random generation. The issue that we have here is a very sneaky issue due to how ECS works. It's one thing that you always have to be very careful with, since a lot of these things are structs, which means they work as copies and not necessarily as references. That's basically the problem that we're getting here. We're grabbing the singleton for the random component and grabbing the random, except when you do this, we are grabbing a copy. So this one gets a copy, then move, this one passes in another copy, so this one receives yet another copy, which then does the random position. So when this one calls the nextFloat function, this is calling nextFloat on a copy. Ideally, this would generate another float and then update the current state on the original random, but since we're working on a copy, this one generates a nextFloat, but then it's always working on the same copy. So the actual singleton object that is never being modified. This is something that you always need to be very careful with when working with dots. You always got to be careful with, are you working with a copy or are you actually referencing the original data? The solution over here is pretty simple. Instead of using GetSingleton, let's use the GetSingletonRW for read-write. This one returns a RefRW, so let's store that instead of storing the random component. So let's store a RefRW of type random component. And we get just this one, exactly like this. Again, it's like this, it's not the value RW. No, let's get exactly the RefRW, that's what we want. Then let's pass that one in. So we just need to pass in this type. So let's go into this one and receive the different type. Let's just rename this to the random component. And then down here, the exact same thing. So in here we use the random component. Let's use the value RW. And then let's grab the random, and then we can call next float. Basically, by doing this, we are always accessing the value RW, which does have an actual reference to the original data. So with this, it should be working, and our debug.log here, this one should always be giving us a different random position. Okay, so let's test. So there's unit going to a random position. Yep, gets there and generates another random. Yep, gets there, generates another random, and so on. So as you can see, now it is always generating brand new random positions. Okay, great. So this was an excellent example of something that you always have to be very careful with when working with dots. You always have to be very careful with, are you working with a copy or the actual original data? Okay, so with this, everything is working perfectly. We have our unit going between random positions, that's great. And so far we made it using the SystemBase, but like I mentioned, for maximum performance, you want to be using the ISystem instead. So let's convert the exact same system onto an ISystem just to see the difference. So over here, let's make a new C# script, call it the moving ISystem. And on this one is not a MonoBehaviour. Instead, let's implement ISystem, which is inside Unity.Entities. Also for this one, since this one is an unmanaged system, that means we need to make this a struct and not a class. Then we need to implement this interface, which involves these three functions, the onCreate, onDestroy, and onUpdate. This is another thing where I think they could improve the API. They could make the interface have default empty implementations for the onCreate and onDestroy. That way you wouldn't have to implement them unless you wanted to do something complex. So basically, ideally, it would work exactly the same as the moving system. Over here, you can also override the onCreate or onDestroy, but you're only forced to implement the onUpdate. So on the moving system, would be nice to work the exact same way, only forced to implement the onUpdate. But as for right now, we need to implement these, but let's leave them as just empty. Okay, so we have our onUpdate. Over here, we can try putting the exact same code. So let's go into the moving system base. Let's copy exactly this and let's paste it over here. And as you can see on the error, all ISystem must be defined with the partial keyword. So let's also add that. So here it is, an ISystem with the exact same code, everything running exactly the same. You might notice that it's running at double the speed. That's because both systems are active right now. One nice thing is on the systems window, which again, you can go into window, entities, and open up these systems. On this one, you can manually enable or disable systems. So for example, I've got the moving ISystem and moving system base, and you can click over here to disable eSystem. So disable the moving system base, and yep, now only the moving ISystem is working. Now I can disable this one, and nope, nothing happens. So just a fun tidbit of information, this window is really very useful. Okay, so back in the code. Like I said, the main benefits of using ISystem is that you are able to use burstable jobs. So instead of running this code, this for each, which is only running on the main thread, instead let's make a proper job that we can then burst and run on multiple threads. To make a job, you make a new struct, so a public struct. And let's call this the move job, and then you implement one of the many job interfaces. For example, you have the IJob chunk if you want to iterate over multiple chunks. And you have the IJobEntity, which iterates over entities. Let's use this one. Now over here, we just implement the public void execute method. Then the job also relies on code generation. So over here, this one also needs to be a partial struct. So we have the execute method, and over here we can include whatever components or aspects that we want. So basically inside of this execute function, we want to run the same thing we were running on the for each. So in order to run this code, we need to have our move position aspect. So let's add this one. So let's add it right here. And then we run the exact same code. So just run this code. This is required that we receive the random component. So let's receive it as a field up here. So the RefRW for our random component. And up here on the update, instead of doing all this, what we do is we construct a new job. So a new move job. We need to set our random component. So let's set the random component and let's grab it. So let's actually run the same as the other code to grab the field, and then we pass in that exact same thing. Okay. So this constructs the job, and then afterwards we need to run it. And again, that's where those options that I mentioned a while ago come in. So you can make run if you want to run it on the main thread, but that would be kind of silly to do if we're working over here on an ISystem. Over here, we want it to make as parallelized as possible. So alternatively, we have schedule. This one is going to run the job on a separate worker thread, but only one separate worker thread. And then finally, we have the schedule parallel. This is going to run on multiple separate worker threads. Then each of those worker threads will then work on a certain number of entities. So for example, if you had 10 cores and 100 entities, maybe each core would run 10 entities, all of them running in parallel. Okay, so with this we are creating and scheduling our job. However, like this, we actually have an issue. You might have spotted the issue already. The issue has to do with, as you can see over here, we are using a RefRW, so we are reading and writing onto our random component, and then we're scheduling it in parallel. If we try running this, and nope, there's our issue. Basically, in order to update the random component, it uses unsafe pointers. And if you do that, then you cannot guarantee that you don't have any race conditions. So you cannot run this job in parallel because multiple worker threads might be both trying to access and modify the same random component. So in this case, what we can do is simply split the logic. For the movement logic, over here, we can easily run all of this in parallel. So we can do this for all entities at the same time. And then after all entities have moved, then we can sequentially test if they reach the same position and reuse the same random component to generate another random position. So let's just quickly split this code. There it is, so the move function only moves, and this one does test if we reach the new position, and if so, generate a new random position. Now here on the system, we can essentially make two jobs, and the second job will just test if it reached the target position. So let's just give it a different name. This one does receive the component, and this one receives just the random component. Then this one up here does not have a random component. And also over here, the system API, we cannot access the delta time from inside of here. So let's do a public float delta time, and we're going to use this. So then up here, when creating a new move job, let's set the delta time. Over here, we can access the system API, time.delta time. Then we don't have the random component. So we schedule the move job to run in parallel, and then we construct a brand new test reach position job. And for this one, we do pass in the random component. And for this one, we are going to run on the main thread. Now like this, we still have some issues. If we try testing, we get the usual message that is really not very helpful, just saying invalid operation, no suitable code. In this case, the reason is because whilst creating the job, over here, we cannot access the system API. We can access it, just not inside the job initializer. So we need to go up here to define a float for the delta time, system API, access time.delta time, and then we can indeed pass in that copy, and like this, it does work. Let's just add a return here, just so we don't see the second issue, just to make sure that this part works. And yep, it does work, it does move. For our final issue, like I said, we want to do all of the move jobs, and then we want to test if we reach the target positions. So we want to make sure all of these schedule in parallel, all of these run and complete first before running this one. So the final thing we need is really just a job dependency. If we look into over here all of the versions for this function, one of them, as you can see, does return a job handle. So over here we can grab the job handle, and job handle is inside unity.jobs. And to return a job handle, we need to use the function that takes in a dependency, so we can access over here the system state. So the state.dependency, that is going to be the dependencies for this job system. Okay, so now the goal is basically we want to run and complete this job before running this one. So one way we can do that is just going to job handle and call complete. That is going to ensure that all of these, this schedule in parallel, is going to complete before we get to this point, which is going to run on the main thread. Okay, so like this, it's almost working. We just need one more tiny thing, so let's test. And there's our final issue, again telling you that unsafe pointers cannot be used, which are used in the random component. As long as you know what you're doing and you're not messing around with multiple threads, you can use this attribute to disable this safety. So since here we're going to run this on the main thread and we know what we're doing, we're accessing the random struct. So we're not doing anything too special. So over here, we can indeed use the attribute in order to disable that restriction. All right, so like this, everything should be working. So we can finally go and see, and yep, the unit does go to direct position, gets there, gets a random position, and always goes from random position to random position. The final thing that we need, which is one of the main benefits of System, is being able to use burst. So over here, let's add the attribute BurstCompile. So we add it over here, then we also need to add it to all the functions. And on the jobs themselves, this one, I'm not sure if you have to add this, but you can also add it. Alright, so now these jobs should be running with burst, which should be insanely fast. So let's test and see. And yep, everything still works exactly the same, and we can even look into nice profiler, so analysis profiler. And over here we see everything running insanely fast, so let's click on a random point. So over here in this case, really need to zoom in order to find it, since we really just have one entity and that's how fast this is. But over here we can see default world moving ISystem, taking 0.02 milliseconds. And if we scroll down, we can find, yep, over here, our burstable move job, completing in 0.003 milliseconds. And then finally up here, as you can see, all of those complete, so that job completes. And then we've got the test reach position job. This one runs after and completes in 0.002 milliseconds. So all of it insanely fast. Even if we were to compare just one entity with one game object, this is still much faster. Okay, so our iSystem works. Here we have the two ways of doing a system. So we've got the SystemBase, we get the onUpdate, and we do an Idiomatic Foreach. And we've got the moving iSystem, which manages to use burst in order to be much more efficient. And for this one, we implement iSystem, and we do things a bit differently by creating the actual jobs that we're going to execute. So for simple use cases where you want to run some code on the main thread, you can use the very simple SystemBase. And for more complex code where you really want maximum performance, just go ahead, implement an iSystem with some jobs and schedule them in parallel. As you can see, all this syntax is actually pretty straightforward once you learn what all of these terms mean. What is a system? What is the burst compiler? What are jobs? How do you get components? And so on. All of it is really relatively simple with the potential of being insanely fast. Okay, so next let's look into instantiating. Let's go into our entity subscene to create a brand new game object. Call this the player spawner. Now let's make a component, so an C# script for the player spawner component. Then over here, as usual, let's make this a component. So first of all, it's a struct and implement iComponentData. Then inside here, let's add a simple entity field for our prefab. So a type entity for our player prefab. Now let's make the usual authoring and baker scripts. Okay, so here I've got the baker. Now the important thing is on the MonoBehaviour, on the authoring component, I made it of type Game Object, but on the component itself, it's of type Entity. So basically we want to convert this prefab into an entity, which we can then instantiate in the entity world. And how we do that is very simple. First, let's add our component. Let's add of type player spawner component. And then over here for the player prefab, how we convert game object into an entity is super simple. We'll literally just call getEntity, and we pass in, go into the authoring component to get the game object player prefab. Okay, so that's it. It's really that simple. Now here in the editor, we have the player spawner. First of all, let's make the player into a prefab. Let's rename this, call it player. Then just drag it over here into the project. And let's get rid of the one on the subscene. So delete it. Then on the player spawner, over here, let's add the player spawner, the authoring component. And then we just drag our prefab reference. Okay, now let's make a system to use this entity and spawn it. So let's make a new C# script for the player spawner system. For this one, we don't really care about maximum performance, so let's use the simpler SystemBase. So let's go with SystemBase. And then over here on update, let's spawn a new player every frame until we have a certain amount. For identifying players, one thing we can do is use a nice tag component. So let's create a new script, call it the player tag. Then up here, let's do the usual thing, except for a tab component, we're going to make this empty. So it's a struct iComponentData. There you go, just like this, just an empty struct. This is our nice player tag. Then we need to attach it, so let's make the authoring. And over here, the only thing we do is just add the component, so just a new player tag. Okay, like this. And now I need to actually fix this error just so we can compile it. So our SystemBase needs to be partial. So just over here, let's make it partial just to make that error go away and our code compile. Now here we can select the prefab, and let's also add the player tag authoring. Okay, so that is going to add a nice empty player tag. And with that, we can basically find all of the players in the world. So you can go into the entity manager in order to create an entity query. Then we pass in the type, so type of our player tag. So with this we have an entity query. And then on this we can calculate the entity count, so that is going to tell us how many players exist in the world. So we can just check if this is under a certain spawn amount. If it is under that certain amount, then we want to spawn a brand new one. So for spawning, one way that you can do it is go into the entity manager and call instantiate and pass in the entity. So we need to get our entity, so let's do it just like we did previously. So let's go into the SystemAPI in order to get the singleton of our type. So our type was the player spawner component. And here we're just reading, so we can use the regular singleton. We don't need the singleton read write. So we get that, and from here we can access the player prefab. Okay, so this would indeed instantiate it. In this case, since we're working inside of SystemBase and running everything on the main thread, in this case this should be working fine, so let's do a quick test. And if there you go, it does work. We do have indeed 2 player units. Okay, great. So this does work. However, one very important concept in ECS is the concept of structural changes. These are changes like spawning or destroying entities, or modifying an archetype by adding or removing components. Basically, you need to be careful with when you do these types of changes. If you do them while some system is cycling through some entities, then everything will probably go wrong. So for spawning or destroying entities, or adding or removing components, to do that you should do it at specific points. If you look over here in the systems window, we see all the systems that we already saw previously. We've got a whole bunch of groups. And then we also have some things called an EntityCommandBuffer system. Basically what you can do is you can queue up some commands to run on one of these EntityCommandBuffer systems. So you can queue up the commands and then they will be executed the next time this runs. Basically these are called sync points. So when adding or destroying entities, when adding or removing components, you should probably be using an EntityCommandBuffer. Which one you use is going to depend on what you're trying to do. In this case, let's use the begin simulation, this one, to spawn our entity. So here, let's do that. So we go into the SystemAPI, then we get singleton as usual. And for now, let's go into the begin simulation entity command buffer system, and let's access the singleton. With this, we have the singleton, and then we can call create command buffer. This one takes a world, and for that, we can use world.unmanaged. Okay, so this is going to return entity command buffer. Okay, so we have this. And over here, instead of calling instantiate directly on the entity manager, which will spawn the entity right away, instead we're basically going to queue up the command. So go in here and call instantiate and do the exact same thing. So instantiate the exact same prefab. Then after instantiating, this returns an entity reference. So entity, the spawn entity. And if you want, you can modify some things. So for example, let's go into the entity command buffer in order to call set component. And let's modify our speed component. So let's pass in a new speed. And for the speed, let's pass in the value and put the value on something else. To add a bit of randomness, let's grab our usual random component. Except since this one needs to update, we need to use the read-write. So the random component, value RW, and then let's grab the random in order to get the next float. And for the speed, let's say between 1f and let's say 5f. Okay, so we're giving a random speed to our brand new entity. We just need to use the entity just like this. Okay, so with this, we should be spawning our entities and they should have a random speed. Let's also just increase the spawn amount by a little bit. Let's say just 20. Let's test. And yep, there we have our 20 players, all of them with some random speed and moving to random positions. As you can see, everything still works exactly the same. So all the systems work regardless of how many entities you have. For one more interesting thing, let's look at how to mix ECS and game objects. So over here, I've got a very simple circle sprite texture. Then my scene, I just created a game object, like a regular game object, not an entity. And inside, just place the circle with a nice sprite render, so pretty simple. And again, this is a regular game object, nothing in here is being converted to any entity at all. So now let's make a nice C# script, call it our player visual. Let's leave this one as a MonoBehaviour and attach it to our regular game object. Over here, let's have a field for our target entity. So private entity for the target entity. And then let's make a function to select a random target entity. So private entity get random entity. Now here we can do similar to what we did previously. So on the player spawner system over here, we're using the entity manager to create an entity query. However, this entity manager, this one is not the static entity manager. This one is a component of the SystemBase. So over here, if we use entity manager, now we're using the class and not any property. So we need to access a specific entity manager, and when we can do that, we can access the world in order to get the default game object injection world. So this is going to be pretty much the default world. In our case, we know that that is the one that we're using. We're not using multiple worlds. So from this one, then we can now get the entity manager, and we can now create an entity query. And let's pass in the same thing. So type of our player tag. So this is going to return an entity query of our player tag entity query. And then from this one, we can call toEntityArray, which is basically going to give us an array with all of the entities that have the player tag. We need to use an allocator. We just need this to be allocated pretty much just once, just as soon as we get the random entity, then we want that allocated to be disposed. So let's use temp, that is the shortest lived one. This returns a native array of entity, which by the way, native array is inside using unity.collections, okay? So we have an array of all our entities. Then let's just check if we have any. So if this one .length is bigger than 0, if so, let's return a random one. So just go in there and just use, now we can use the regular random.range because again, now we're in MonoBehaviour world between 0 and the entity native array.length. And if there are no entities, then we can return the default, so the entity.null. So this is the constant that always refers to an empty entity. Alright, so now we want this player visual to basically follow our random entity. So let's make a private void late update. We want to update the visual after all of these systems. Then in this one, let's check if the target entity is not null. So if it is not entity.null, if so, then we want to follow. So we need to get the position of this target entity. And again, how we do that, let's access the world to go to the default world, access the entity manager, and from this we can call getComponent. And we need a component of type that has the position, so we can use the local toWorld transform. We need to pass in the entity, so that is going to be our target entity. And from this one, we can access the value and then access the position. So that's a vector3 for the follow position, which actually is not a vector3, rather a float3, but those two get converted automatically. So we have our follow position, and then we just set this transform.position equals this follow position. Alright, so with this we should have a nice connection between the game object world and the entity world. Let's just define how to set the target entity. So let's do some simple input. So input, get key down. So when I press the space key, then let's get a random one. So get a random entity. Alright, so let's test. And yep, it is indeed working. So again, here we have our circle visual, which is a completely normal game object. So there's nothing related to entities on this game object itself, a regular game object. So that one is managing to interact with the entity world in order to follow an entity as it moves. So you can see how easy it is to mix game objects and entities and access anything from the entity world while the game object world and vice versa. Here note how I did it this way. I basically made a MonoBehaviour, and from inside this I access the entities world. But you can also do the opposite. So on some kind of system base, so something like this, you could make a system, then over here access some MonoBehaviour, perhaps through a static field, access that and then modify that over here. So you can do both. You can grab the game object world from the entities world, or you can grab the entities world from the game object world. Finally, let's do some performance comparisons. So here I've got two simple MonoBehaviour scripts running the exact same code. First of all, a player spawner game object. So I just have a reference to the game object prefab, which by the way, I'm actually reusing the exact same prefab, even though in MonoBehaviour these components won't do anything. So I got that, then I just cycle through a certain spawn amount, I call instantiate on prefab, then I add my game object move to position component, and I set a random spin. So for this component, here it is, again, just regular game object code. I've got a target position and a certain speed, then on update, call the move function and the test reach position function. Then over here, pretty much the exact same thing, except using vector3 instead of float3, and for the randomness, using UnityEngine.Random instead of the Mathematics.Random. So there you go, as you can see, pretty much exactly the same code. And yep, here it is running. As you can see, everything looks exactly the same. Looking in the hierarchy, we can see all of these game object loads. Now let's increase the amount by quite a bit in order to bring the FPS down. So here, let's try increasing the spawn amount to 10,000. So let's see. And yep, here we have 10,000 game objects, and it's running at about 40 frames per second. Looking over here in the inspector, it seems that all of these 10,000 are taking up 10 milliseconds. Then the rest is related to rendering, which is taking another 10 milliseconds. Now let's bring the game objects back down to 0, so spawn no game objects. And on the ECS player spawner system, let's put this one on 10,000. So let's see. And yep, there we go. Here we have 10,000 entities. We can see down here the moving ISystem is accessing 10,000 entities, and the frame rate is around 120, 140 FPS. And looking over here in the profile, we can see quite a big difference. So we really have to zoom in order to see just how much. So the entire simulation system group is taking just 0.4 milliseconds, and the presentation system group another 0.4 milliseconds, and then over here for the rendering, 2.5 milliseconds. So previously we had 10 milliseconds on the logic, and now here we have less than 1 millisecond on the logic. So as you can see, this is the kind of performance that you can get with ECS. It's a pretty massive difference. And hopefully with this video you saw that the syntax for dots really isn't that much more complex. I mean, it's definitely more complex than a regular MonoBehaviour, but nothing too intense. Once you learn the main concepts, everything is actually pretty intuitive. Now, even though this video actually ended up being a lot more detailed than I initially anticipated, even with that, there's still quite a lot of things that I haven't covered here. If you want to continue researching dots in more detail, I can highly recommend their official tutorial guide. Over here you've got introductions talking about all the concepts, and then you even have some really nice, really in-depth tutorials to learn absolutely everything. Then of course you have the entities documentation. Over here there's lots of great info to help you understand all of the various concepts within this. And if you want a full-length project, then I can also recommend the excellent 2-hour video by TurboMixGames. It's building a real nice project involving tons of concepts and putting it all together. Also, you can follow his channel if you want to keep up to date with dots until 1.0. There's links all in the description, and I hope this video gave you a nice overview of the current state of the API and how it all works. Personally, I think it's all pretty intuitive and easy to use, so I'm very much looking forward to the future as dots hits 1.0 and regular people start using it to build all kinds of very interesting and very ambitious games. Speaking of that, go ahead and add my game to your wishlist. I'll probably be using dots for some systems and making some nice devlogs from it. Or if you want to learn Unity in general, check out my complete step-by-step courses. Alright, hope that's useful. Check out these videos to learn some more. Thanks to these awesome Patreon supporters for making these videos possible. Thank you for watching, and I'll see you next time.